Hi and welcome. I am August Christopher and De La Torre, and I am a third year science major education student in Central Bicol State University of Agriculture. And today I will be tackling about the Louis de Broglie wavelength, or the Louis de Broglie equation, which is expressed as the lambda, or the Louis de Broglie wavelength, is equals to the Planck's constant h over the symbol rho, which is the momentum. Or it can also be equated as h, which is the Planck's constant, over the m, which is the mass, and v, which is the velocity of a certain particle or a matter. So without further ado, let's have a quick background check to the marvelous physicist that discovered this equation. So in the 1920s, Louis de Broglie made a bold assertion in his doctorate dissertation. So when he was taking his PhD, he thought of this. He thought that all matter has a wave-like property. And this bold assertion was inspired by the German physicist Albert Einstein, when Albert Einstein discovered that light, as we know in our classical physics, is only a wave. And Albert Einstein seemed to prove that it is also a particle. So, with that, the birth of the wave-particle duality of light has been recent, and ever since, light has been seen as a particle, and it has a discrete amount of energy that can be quantized through this equation. E, pardon, E, or the energy of the photon or the particle of light, is equals to the Planck's constant times nu, or the frequency of the light. And thus, our scientist Louis de Broglie also thought that if light has a wave and particle duality, so can electron, because electron is also a particle. And he thought that this particle, which is the electron specifically, can also have a wave-like property. So with this equation, the energy of the photon and the momentum of the photon, which is expressed as the momentum of the photon, is equals to its energy over the speed of light. So these two equations de Broglie used to find the um, wavelength of any particle. So with that, we can tackle that in another video, but for now, let us focus on the Louis de Broglie wavelength itself. So this equation, or this assertion that electron is a wave, was supported by two more scientists, which is Davison and Germer, which they conducted an experiment proving that electron really does have a wave-like property. And they observed a diffraction pattern or interference pattern in their experiment when they fired an electron to a crystalline nickel target. And they were given a Nobel Prize in the 1937. So with this, we can see that the relationship of the de Broglie's wavelength to its momentum is inversely proportional, which means that when the mass and the velocity of a specific particle or matter goes up, its wavelength will go down. So the quantity of the wavelength will go down. So vice versa, if the mass and the velocity of a specific particle or matter goes down, so it becomes smaller, then the wavelength of that specific object will go up. So it will be more noticeable in that specific scale. So relative to the Planck's constant. So now for us to furtherly understand, let's have a sample problem to solve for this case. And now we have problem number 1, and it says that a baseball was pitched by a pitcher with a mass of 0.145 kilograms with a speed of 40 meters per second. So what is the de Broglie wavelength of the ball? So now first we will have to look at what are the givens. So the lambda is what we're looking for. We already have the mass, which is 0.145, and it is already expressed in kilograms. And we have the speed of the ball, which is 40 meters per second. And we have the Planck's constant, which is h, which is 6.63 times 10 raised to the negative 34 joules per second. So now we can plug in our given to the formula with our solution. So lambda is equals to h over mass times velocity. Lambda is equals to 6.63 times 10 raised to the negative 34 joules per second, or we can also express it as kilograms meters squared over second squared times second. So it is all over the mass, which is 0.145 kilograms times 40 meters per second. And now, let us compute it using our calculators. And I believe that in order for us to get the wavelength, the unit that must be isolated is the meters, because the wavelength is the measurement of the how long a wave is in a wave. So let us cancel out the units. So first we have kilograms, and then our seconds will cancel out, the meter will cancel out, and then this last one will be cancelled out. So the unit that is left is meters. So our cancellation is correct. So I believe that the answer to this equation is 1.14 times 10 raised to the negative 34 meters. 4 meters. So this is the wavelength of the ball. And as you can observe, the wavelength of the ball is very, 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 very small. Because of this expression, it is raised to the negative 34th of a meter. So if we're gonna convert this to nanometer, which is the general measurement of the quantum realm, this would be 1.14 times 10 raised to the negative 25 meters. I mean nanometers. So this is still very small in compared to the electrons, the wave of the electrons that can be seen. So therefore we can conclude that even though we are matter and we are composed of this wave property, we can't see it because it is very small. And if we are going to compare this to the diameter of a hydrogen, which is only 1.2 times 10 raised to the negative 10th meter. So if we're going to convert this to nanometer, it's going to be 1.2 times 10 raised to negative 1 nanometer. And this can be already seen in an electronic microscope. So yes, That's our first problem, and I'll give you another problem for you to solve, which is this one. So now it is your turn to answer this problem, and I hope you compare it to our first, to problem number one, because problem number one has a larger mass, and this one is this one has a very small mass, which is an electron.